That's sort of where we were yesterday, and today is going to be kind of similar, but kind of different at the same time. And this is taking isotopes rather than just looking at an individual consumer's diet to blow it up a bit and see what can we say about a whole food web and food web structuring using isotopes. And this is a field, or again, similar to the mixing models. As the softwares come on and as the statistical packages have become available, this is a component of isotope ecology which has really grown a lot in the last 5 to 10 years. And what we can be done now as in 10 lines of OR script was, we couldn't have dreamed about it when I started doing this in my PhD years. So I'm going to start a little bit of theory, a little bit of conceptualizing behind what I'm going to talk about later on first, and what do we mean, or in terms of trophic ecology. I know some people here know exactly what I'm talking about, some people here don't. So just a couple of slides just to bring everybody up to a standard level, and we can work from there. So I'm going to talk quite a bit today about an organism's trophic niche, and essentially what I mean is the breadth and type and diversity of different things that it eats. And that can be made up of a number of different things. An organism's trophic niche is defined by a number of different things, and one of the main things is the trophic level the organism is feeding at. So here, and similar to what we saw yesterday, as we move up from primary producers, primary consumers, secondary consumers, tertiary consumers, and on up a food chain. And this, as we saw yesterday, can be nicely reflected in the delta 15N values of consumers. So as well as knowing this from all data and stomach content data and archive data sets, things like that, we can also infer this and visualize this through isotopes and visualize this on an isotope biplot in delta space, in isospace. An organism's niche, as well as its trophic level, is also defined by the types of things it eats. So you can have different species who are feeding at the same trophic level, but use feeding on different resources. And again, this maybe links in with the carbon axis. This is x-axis on our isotope plot. So you can have different resources, and different consumers are feeding on these different resources. And once you have a marker, be it a carbon marker or in a estuarine habitat like this, maybe a sulfur marker, that can distinguish between these different primary producers along this region, then you can distinguish between these basal energy sources. Well, organisms in terms of their trophic niche are also defined by, or also characterized by their niche width. And this is something we'll talk about a lot today. And quite a bit of my work revolves around this idea of niche width and looking at niche width in different systems. And there's generally specialist. Generally, species can be classed along a spectrum running from an absolute specialist, which will only feed on one or two types of prey, so then herbivore, to an absolute generalist with a broad niche width, which will eat anything you put in front of it. And this is reflected often in morphological adaptations to specializing on one type of prey, or to being able to feed on a variety of different prey. It's reflected in where organisms can reside. A pelagic specialist fish will generally only be found in a pelagic zone, whereas a generalist fish might be able to forage across pelagic and benthic zones. And when we build this up into a food web concept, so we can see how these three different factors within a trophic niche play into constructing a food web. So we have different trophic levels here from primary producers, secondary producers, and so on. We have different basal sources. We have different productivity sources from this pelagic component of a food web and this benthic component of a food web. And then at the top, or all the way along, we have species that exist on this gradient from specialists to generalists. So again, we've got pelagic specialists here, benthic specialists, generalists, which are foraging off pelagic or benthic fishes, or benthic preys. So within this food web is constructed of a number of different consumer groups, which all have their own unique, or their own distinct trophic niche. They don't necessarily have their own unique trophic niche, but as and where niches do overlap, but the species will have their own defined niche within a food web. So this has been known for a long time, and it's not just somebody came along with stable isotopes and showed this, but it's a neat way of characterizing an ecosystem and trying to understand what different processes have on an ecosystem. If you get climate change, which increases the pelagic productivity, what effect will that have on a food web? If you get an invasive species comes in and eats all these precious specialists here, what effect will that have on the food web? If you get overfishing and you cut out all these top predators, what effect will that have on the food web? So this food web analysis is a nice way of looking at the effects of these different anthropogenic stressors, things that people do to the environment, or natural effects that happen to the environment, and what effect that causes on species residing within these systems. So traditionally, how a lot of people analyze this was just looking at stomach content analysis, dietary analysis, and through this they can build links between species A, species B, species B, species C, and so on. But there's been a push, because we know we can characterize this food web using stable isotopes. There's been a push in the last 10 to 15 years to try and find a way of numerically characterizing this, rather than just saying, okay, well, we can visually see how it works. How can we actually put numbers on it and analyze it? And this came through. This was mainly an idea that was proposed in a review paper from, again, some of the same names we heard yesterday, people like Seth Newsom, Don Phillips, Stu Beerhop. And this was around about 2006, 2007. I came to this yesterday. The Ecology, a special issue was produced. Brian Fry's book came out. I started my PhD. That this was a really hot time for stable isotopes. There was a lot of neat work being done, or a lot of neat work had been done, and maybe the second generation of people were coming along and looking at it and approaching it with a different mindset, and the analysis had gotten much simpler and much cheaper, so it was much easier for people to generate big data sets within a single project. So two papers around about there in 2007, and this one is a niche for stable isotope ecology, and it's kind of a review paper, but a lot of the things they talk about in it is how to characterize an organism's niche, but using stable isotopes. And rather than looking at niche width here, they're really looking at these metrics, or these ideas that I said earlier, looking at trophic level plus resource use plus niche width. At the same time, this guy Craig Lehman and a couple of others, David Post, who we also talked about yesterday, came up with these metrics to measure food webs using stable isotopes. And that was a really big breakthrough for this side of isotope science. So to start at the start a little bit, and basically what they're saying is, okay, so we want to examine consumer niche width. And this is the typical isotope bite plot that we looked at yesterday, where you've got your pelagic productivity, benthic productivity, pelagic consumers, benthic consumers, and generalists in between. Well, that's a very simplified visual thing. What you've actually got is a series of data points, a series of individual fish. And as you plot up your individual fish, they will have a specific dispersion, a specific range. And that's your pelagic specialist will all be tightly packed around this zooplankton value. The carbon value will match zooplankton, the nitrogen value will match zooplankton plus 3.5, give or take a little bit. we look at the other side of the food web, the benthic side, your benthic specialist fish will have the same thing. Their carbon range will be restricted solely to this benthic carbon, and their nitrogen range will be pretty much primary consumers plus or minus 3.5, or plus 3.5, plus or minus a little bit. But you're the generous consumer, what's feeding in somewhere in between, and it's getting carbon resources from the pelagic zone and also from the littoral zone. If you plot a number of these fish, you get generally you might get a larger dispersion. You might get all the fish just might be slap bang in the center there. What does that mean? So all the fish are you've got this generalist fish, but when you plot up 20 of that fish, they're all just sitting dead smack bang in the center of your carbon 13 range. What does that tell you?
50% of bones.
Exactly. Yeah, yeah. So if you've got a system like this where they're much wider, what does that tell you?
Got a mixture of specialists on different things.
Exactly. Yeah, yeah. So you've got so you can have a generous population, and that generous population can be that they're all generalists. If you get 50 fish and they've all eaten 50% of this and 50% of that, or they could be that this fish is predominantly eating pelagic, this fish here is predominantly eating benthic, and you've got a dispersion of a range in between. So this is another, when you look at this consumer niche width, you remember that you're looking at two different things. You're looking at a population level niche width, but you also have to factor in the individual level niche width, or the individual resource use. So to get back to Craig Lehman's stats, or this, we're going to talk about Craig Lehman. What they wanted to do was to take things a step further and say, okay, well, we know we know we've got our isotope plots. I mean, this is our typical food web, carbon 13, carbon 15, and different consumers, maybe even primary producers, some consumers and some predators higher up. So how can we put a measure on this food web? So he developed these 5 different metrics that you can use to numerically characterize a food web. And the first of these is this NR, which is 15N range, and that's basically the difference between the highest and lowest number of the food web in delta 15N. So that's giving you the full range of values. The CR, the delta 13C range, so that's the difference between the highest and the lowest delta 13C values. So that's giving you the full disparation, or the full range of energy sources and resources that are coming into the food web. TA, which is total area, and this is a convex hull or a polygon which covers all the outer members of the food web. Yeah, so it's essentially a measure of the size of the food web in delta space, in isotope space. Then CD, mean distance to centroid. So if you plot a centroid, if you plot the mean of means, or plot the mean of all the different consumers, all the different populations in your community, and then the distance between each one of those and your centroid. If you have a very tightly packed community, or a very tightly packed system where everything is feeding on the similar resources, there isn't great diversity of resources, you'll have a very low mean distance to centroid value. If you have a bigger system where you've got a number of different sources or higher consumers, that value will be greater. That distance to centroid value will be greater. The mean nearest neighbor distance, so that's essentially the distance between, in isotope space, between one population and the nearest population to it. And again, this is kind of another measure of food web packing. how closely together the different consumers are within the food web. And then finally, he's looked at this standard deviation of nearest neighbor distance. And again, that's another measure of food web packing. And these, there's now six, is there six? Yes, there's six. These 6 metrics have become vernacularly known as the layman metrics, or the layman statistics. And they're, since he published that, that's been really widely used. And allows isotope ecologists to put metric values on their food web. So one of the good things about being able to do this, so I talked earlier when we sort of plotted up that graphical image of a food web, that we'll want to examine what happens if you affect different stressors within that food web, if you add a new species, if you take out a source, if you warm everything up, whatever. So this, again, is sort of Rob the plot out of his paper. So this is his standard food web here, with carbon, nitrogen, some different producers, some different consumers. So you look in hypothetical example 1, a new invasive species comes in, a new top predator comes into the food web. So if this is maybe your before and after study. So what happens to your metrics then when you analyze these? So your NR, your nitrogen range, has increased. You've got a new consumer in your food web. So you can metrically show this, how this has affected the food web size. The TA, a convex hull around all components of the food web, that will also increase. The centroid, the distance to centroid, will also increase because you've got a new outlier group, say. Your nearest neighbor distance and standard deviation of nearest neighbor distance, they'll then decrease. So your food web isn't as tightly packed as it was before. What happens if you get a new primary producer, a new type of resource comes into the food web? And this could be say marine-derived nutrients, something like that. If you get this is your normal river your normal river food web here, say, and this is when a load of salmon spawn, or when somebody opens a mink farm in an accompanying island, or something like that. You get this new resource coming into the food web, and what effect does that have at a food web level? So it doesn't make any difference in the nitrogen, because you don't have a new top consumer or a new lower primary producer coming in. But it'll increase the carbon range, it'll increase the convex hull, or the TA, it'll increase the centroid distance. Then similarly, what happens if you get just another maybe an invasive species scenario again, that you've got a series, you're in a lake and you have a nice simple fish community in your lake, but somebody introduces brook trout or roach, if it's in Ireland, as an invasive species. They come in and they sit in the same trophic position as one of the other consumers already in your food web. So it's not going to change the overall food web size. I mean, no change in these nitrogen range values or carbon range values or total area values. But there will be a change in the distance to centroid. That will decrease because your food web is now more tightly packed. And again, that's represented in your nearest neighbor distance and standard deviation in nearest neighbor distance. So this is, again, to the risk of repeating myself, this is really, it allows us to put a metric value on what's happening in an ecosystem, in isotope space. And it's, to play devil's advocate a little bit, you shouldn't, and we can talk about this, I don't have any slides on it, but we can talk about it later on if we want, that there's a danger of thinking that isotope space directly reflects real world. What you're actually looking at here is isotope ratios. And you all, again, come back to this, know your system, know your data. It's up to you as the researcher to make inferences about what these isotope ratio values mean to your system.
So this may be tied to that, but like, what's the ecological function or consequence or implication of having like a large that people have measured how that affects whole ecosystem processes?
Yeah, so that's again, so for the webinar folk, just to repeat the question. So the question was, what's the effect of, if a new consumer comes in, let's say in this third scenario here, something like that, where you've got just a new consumer has come into your system, but it hasn't directly affected any of the food web size, but it has affected this sort of how tightly packed the food web is. So there's a number of pretty serious implications. Like, one is if if you're dealing with a system where prey resources are limited, like an oligotrophic lake or a clean water river, and you get a new invasive species, a new consumer comes in, it's directly going to be competing, or it may directly be competing for resources with the resident fish. So that will be visualized here. So if you plot up your food web and your isotope food web as a before and after, and your food web size won't have changed, but you'll be able to see that. So you've got this new consumers come in, these little black dots, and you can say that whether it's using the same resources as our pre-existing species or our resident species, and if you've got associated with this some decrease in condition or decrease in reproduction of your resident fish, it's more evidence to support the case that it's an ecological consequence of this invasive species coming in. That's one example. So this is a couple of different things. Okay, so this is Craig Lehman. I think that's a wonderful picture. This is Craig Lehman, and this is one of the places he works. That's as far as I'm concerned, that's what happens to people who write great isotope papers. Whoops. So one of the first in 2007, he wrote two very important papers. The first was this one. The second was this one, where he used his metrics to analyze the effect of ecosystem fragmentation. So it's one of these stressors, doesn't really matter what stressor you choose, on a food web. So this is the system he's working on, and it's these nice islands in the Bahamas, and I think in something to do with development, that basically they're breaking up this area, this coastal margins area should all be one zone, but through some development that it's been broken up, fragmented into different zones, that there's less freedom of movement for consumers around the island. This is the food web in a non-fragmented system. So you have a large diversity of different resources, you have a multitude of different intermediary consumers, and then your top consumer, I think this snapper that he was working on, this is their trophic position as the top predator controlling everything around their island. So if you look in the more fragmented food web, and the more fragmented areas, that the diversity of prey types or resource types is limited. The amount of intermediate consumers as a consequence of that becomes limited. So the trophic position then of your top consumer drops down. And this is a hypothetical example. So this is what he predicted to expect, or what they expected to find. And he used then his Lehman metrics, or the metrics that he devised to test this, and use this as a test of the metrics. So what we see here is start at the start. So this is an isotope, a delta space representation of this plot here. So in your unfragmented system, you have quite a nice diversity of carbon sources, a multitude of different intermediary consumers, and then your top predator here. In your fragmented system, you've reduced the diversity of different carbon sources, reduced diversity of different intermediate consumers, and this is your top predator here. But if you compare the metrics, say, between these two systems, we see that the nitrogen range decreases, the carbon range decreases, the total food web size decreases, the distance to centroid also decreases. As you've got less things in your food web, say. The nearest neighbor distance increases, and the standard deviation of nearest neighbor distance increases, again, because you've got less groups in your food web, so there's a bigger area between them, say. So this is essentially it's a measurable effects of fragmentation on the food web. So you can measure, you can get a value behind just saying, look at this pretty diagram. This is what's happening. You can go and put numbers on it and quantify it and convince people who aren't convinced by pretty pictures but are convinced by numbers that there's something actually going on here. Yeah.
To me, those graphs, when I just look at them, the first impression I get is that the lower half is gone from the left one. Is it possible that the consumers are just ranging further than the study space to find the more, because the levels of the top consumer there look like about the same.
Yeah. So what you've got is the level of the top consumer, the nitrogen level, say, of the top consumer is equivalent, but it's what they've lost is this diversity of different prey sources. Yeah.
How do you know that they're not just ranging farther than those?
Because they did a good experiment and they went and properly quantified their study system. And again, this is what it comes down to. This is when you get results like this. One, you have to be able to convince yourself that this is accurate, and that can be easier to do than it should be. But you also have to convince your external examiners and hopefully your reviewers that this is not only accurate, but it's robust. And if you want to publish it in like the top journal in the field, then it's going to have to be solid. And if you're going to, in addition to if you're going to produce something that's robust enough to give more than just a better quantification of your study system, but that you can build an ecological concept on, you need to have that as much certainty in your methods and in your results or in what you've done as you can. And that's like, this is all great and this is all wonderful and you can build fantastic plots and make fantastic inferences, but the four words are the same: bullshit in equals bullshit out. You know, if you don't, you need to have the groundwork in place. You need to have everything in place before you can make more inferences. And again, this is so we talked a little bit when we came back from lunch yesterday.
Quick question. Like when you look at the fragment, you said you obviously have smaller groups in the unfragmented. But if you found a fragmented space that had the same number of groups as the unfragmented, do you think you would see a different pattern? Like, do you think it's just the fact that you've got the lesser groups that it's?
I think what it is that you've lost this diversity of primary producers in the fragmentation. A consequence of the fragmentation is that you lose these diversity of production types. Yeah. So once you've lost that, you've cut this component here out of your food web. And when you cut that out, then what you're left with is a condensed, restricted food web, or sort of this half here gets shifted over, and you end up with something like that. Yeah.
But it does look from that second diagram as though this lost primary producers altogether. And then there's nothing below 5.
Yeah.
The 2 to 3 range, which is presumably what
I think so. I think what we've got is this one little box here. I think is one of them. So we can sit there. We can talk about the intricacies in this example.
But what I mean is, does that mean that some primary producers have much higher delta 15M ratios than others?
Yeah, yeah,
So,
and
so
they
you can't just look at that value and say what it's doing. You have to know that from your understanding of the system.
Yeah. So you'll need, so different primary producers will have, so I'm pretty sure I didn't plot the legend here, but I'm pretty sure that blocks are as primary producers, diamonds are primary consumers, and then the black diamond is his piscivore. So here you've got a couple of, one or two blocks that are sitting here around about 5. Potentially there's something else missing that's down here. But again, if you're looking at, and it's again where it comes back to this know your system, if you're looking at herbivores, quite often fractionation in nitrogen values for herbivores can be as low as 0 to 1. So if we see, like, there's some work, Tim Jardine, who was in worked in the Sin Lab long before I came here. He has a couple of papers looking at invertebrate communities in rivers around New Brunswick, and has found for primary consumers, herbivores, obligate herbivores, that their delta 15N fractionation values are really, really low. We found something similar in some rivers in the Bay of Fundy. So this isn't totally infeasible, but without having the raw data here, it's difficult to give a detailed interpretation or detailed analysis of this particular set of data points. But essentially what it is a proof of concept, showing the concept. And this is one example of it. If you want to argue whether his hypothesis here that this is a fragmented system that actually has a smaller food web size or not, that's something you can do. And one of the reasons you can do it is because you now have these metrics that you can put a measurement on, and you've got something to argue about. Whether that's how accurate or not that data is doesn't, to my mind, doesn't diminish the benefit of the tool, the benefit of the metric. What does limit the benefit of the metric? We'll get to in a minute, and that it links quite closely to this. So one of the other things he did was looked at the niche width as TA. So we talked about TA being this measurement of the full food web. He also did it as measurement of using niche width of the consumer. So we've got completely non-fragmented system in white dots or white triangles, a partially fragmented system in the gray triangles, and a fully fragmented system in the black triangles. And rather than, and this is just for the consumer, just for the fish. So what we've done is, rather than putting a convex hull around the entire food web, he did it just around the values for that fish, and said, okay, well, this in delta space, in isotope space, is the food web size of that fish. And he then plotted that against the percentage fragmentation in the habitat, and found that, okay, well, in addition to seeing a decrease in total food web size, we also see a decrease in niche width as inferred from TA, total area, of the top predator. So that's and that was a big set. It was one of the first times that somebody had come up with a way using isotopes of defining a niche width and defining a change in a niche width. And it sort of took off. A lot of people used it for a couple of years. but it has one inherent flaw, and that is that it's highly sensitive to sample size. Similar, if you were to measure consumer niche width on stomach content using like a Levin's index, where essentially you just take your population and measure all the different types of things that your population is eating. Here, you take a population and you measure the disparity of isotope ratios within your population. But if you, so you can put a nice little hole around it, but if you sample 50 fish from that population instead of 25 fish from that population, you're getting a bigger number. You're inflating that value, and it's got nothing to do with whether that population is feeding on more resources. You're just including more outliers, including more variability, so you get an increased niche width. So you need to standardize your niche width, standardize your size, your sample size, before doing any of these calculations, certainly if you wanted to use this convex hull approach. And it also leads to the question, well, what's the true niche width for your population? Do you have to go out and sample every individual and get a convex hull of that? And then you've got every individual, so then you've got the full niche width of that population, but that's not really feasible. So then the story shifted a little bit later, and this is, 4 years later, this paper came out from an Irish guy, and this, again, the same guys who developed the SIRE model. So they came up with this neat way, and a different idea, to measure it using a standard ellipse. So this is, you take a univariate distribution, which is one axis, and a series of values, and you can get a standard deviation on that range of values. Yeah, and you could plot that as a line. If you have bivariate data set where you have a series of data points going on two axes, and you plot the standard deviation of your y-axis, the standard deviation of your x-axis, you can generate this ellipse. Essentially, it's standard deviation in two-dimensional space. So what that does is that reduces the influence of sample size. It's a better measure of just looking at the of the realized niche, maybe you're not limited. You reduce the influence of outliers on your measurement. So if we look at a couple of things they did in this paper, they produced this standard ellipse area, which is, as I said, just a standard deviation and bivariate distribution. They also created this SEAC. So SEA is standard ellipse area. It's these ellipses. Excuse me. The SEAC, which is a small sample size corrected standard ellipse, and because they're Bayesian guys, they created this Bayesian standard ellipse area. And here in these series of plots, we have the number of points, number of runs, and the ellipse area, or the estimated ellipse area minus the actual ellipse area. Oh, sorry, this is the number of points in your sample. Yeah. So this is if you have 10 individuals and you've tried to quantify it off 10 individuals, or 100, 10 individuals, or 100 individuals, or 1,000 individuals. So essentially, this is saying how many individuals do you need to get an accurate reflection of the standard ellipse. So for this two-dimensional standard ellipse, our standard deviation, we need 20 to 30. For the small sample size corrected, or SEAB, you can get away with far fewer. So again, it's a measure of getting away with a smaller sample size, or resolving or reducing the effect of an increase in sample size. Maybe that's a better way of putting it, rather than saying that you can use a smaller sample size, but it reduces the impact of a larger sample size. So this paper came out, and a lot of people started using it. But the story takes another little twist. But it states this guy. So REE Silver Hunter is a Finnish guy who is he's a brilliant isotope ecologist and a brilliant fish biologist, and it tells you a lot about the state of funding for science in Europe, that he's now training to be a lawyer in Denmark, which is a shame, but there you go. So what Jari did, Jari worked with Roger Jones, who was maybe the Finnish equivalent to a Rick Kunjak, or the English equivalent to a Rick Kunjak, who lives in Finland and has his own isotope lab. And Jari was one of his PhD students, and later a postdoc in his lab. So Jari was looking at a lot of different things, but one of the things he was looking at was feeding relationships and feeding ecology of two different fishes in this eutrophic lake. This is Jyväsjärvi, which is a lake just beside their university in Jyväskylä in central Finland. And the two different fish species of fish he was looking at was this perch, a typical, like this is Eurasian perch, same as the yellow perch you have here, and roach, which is probably the most common fish in Europe. It's just a standard cyprinid, eats pretty much eats everything. So one of the good things about doing your PhD and then your postdoc with your own isotope lab is that you generate a lot of data. So over a number of years, he already had run hundreds and hundreds of these roach and perch samples. So he had a really good data set to say what happens if you increase your sample size from a very, very small number to a number in excess of anything most people doing stable isotope studies are ever going to have to handle. What effect will this have on these measures of niche width? Which measurement holds up best to variations in standards and sample size? So we decided to compare this TA, the traditional layman measure, with the various different ellipses that the cyber folks had developed. So what we see here is area on the y-axis, so niche width. So that's either TA, the total area in the hole, SEA is the standard ellipse area, or small sample size corrected standard ellipse area. So we start onwards. So we've got perch here, roach there, and the different lines represent different confidence limits. But essentially what we see is that the TA, if you look at this, the total area, and as you continually add more samples, your TA value constantly increases for both species. It never reaches an asymptote. So, and that makes perfect sense, because you're not including any error term. You're just saying, okay, we've got more. You're just including more outliers every time, or the potential for more outliers every time. You looked at the SEA, so this is just pure standard ellipse area, and found that it hits an ellipse, or sorry, hits an asymptote at around about 45 to 50 fish, 45 to 50 individuals for both roach and perch. With the SEAC, the small sample size corrected value or measurement, it reaches its asymptote at around about 20 to 30 individuals. So that's become a standard measurement for, and again, it's the way these things go, that somebody does this on one data set for a couple of fish in one lake, it becomes the standard for people who use it for pretty much everything. That if you want to quantify the niche using this SEAC, you're looking to get at least 20 to 30 individuals. So if you're doing a study and you've got 15 fish or 15 birds, and you want to say, okay, what's our niche width based on that? You really have to start thinking about how valid your values are, whether you can get any more data, or whether you can actually do this. So that leaves us with, I've put this up. This is something that some people do. I don't like it, but because some people do it, I'll let you hear about it and you can make up your own mind. There's an idea at the moment that you can plot, get a population, plot the total ellipse area, and then plot the standard ellipse, the SEAC or SEAB, the Bayesian version. And that the TA, total ellipse area, you can call the total available niche, the diversity of different prey types that your population could be eating or is likely to eat. And then the SEA is the realized niche. It's where the majority of fish or the majority of consumers are sitting within this niche. As far as I'm concerned, this TA is susceptible to bias. So if it's not a good measurement, it's not a good measurement. Don't include it. But there's an argument both ways. So if you want to do it, that's up to you. So the other neat thing that the cyber guys did was so Andrew and a couple of the guys he works with are Bayesian modelers. So they built a Bayesian framework to estimate the Lehman metrics. And essentially what that does is, so this is a, say here, take as an idea that this is two different convex hulls based on, so we've got carbon and nitrogen, different consumers or different populations in our food web, and they're denoted by different markers. You can build convex hulls based on the means of these two different of all these different consumers or different populations. So that's, if you were to do that with the Lehman metric, you could get for these two different populations plotted on the same plot, you could get these two different convex hulls. So what they did instead was they used a Bayesian framework to basically do this calculation in a Bayesian simulation where you do it tens of thousands of times and get tens of thousands of potential hulls, and then see which of those are the most common. So similar to how you characterize the difference between using the characterizing resource use based on the maximum likelihood models and the Bayesian models. So one of the beauties of this is that it lets you can calculate the Lehman metrics, but you can also calculate them with an estimated error. And this again is these same plots that I discussed yesterday, where you've got the mode value at the center, make sure I get this right, 50% credibility limits, 75% credibility limits, and 95% credibility limits. So what that means is that you can characterize your niche width or your food web size or whatever these metrics you want to look at with an element of error. So you can now compare and contrast two different food webs. And if you've got food web 1 versus food web 2 and you've got a difference in TA, if you just use that initial Lehman metric, you just have two individual measurements. You've no way of calculating the variance on that. But with this cyber method, you can now put an error message into, or an error component into that, and say, okay, well, we've got at a higher level of probability or higher level of likelihood that these two different metrics are actually different, or these two different food webs actually have a different size. And because he's an absolute legend, an absolute hero, Andrew Jackson is also, as well as developing all this software, also through this is his TCD webpage or web address, and just Google his name, After you get through about 5 hits for an American president, you'll finally hit this. But basically, he has a lot of different podcasts where you can go in and watch the stuff and watch him give a demonstration of the software. And that is pretty much what I'm going to do in a little while. We're going to break for maybe 10 or 15 minutes if people want to just have a little rest. And when we come back, I'm going to do a little demonstration of cyber, how it works.